This question asks us to design an inverting amplifier circuit to have a gain of 12, and we're told to use plus minus 15 volt power supplies. So the inverting amplifier circuit, the one that we studied in the previous video, has two resistors, and they are connected as follows. And there's input voltage, which is defined with respect to ground. So our input voltage is, let's call it VI, and there's an output voltage VO, and we have 15 volt power supplies. So we have 15 volt rail at the top and a negative 15 volt rail at the bottom. The resistors are called RS for source and RF for feedback. And so this is the inverting amplifier circuit, and we just discovered, or we just analyzed the circuit to determine that the output voltage, V out, is negative RF divided by RS times the input voltage VI. So that's kind of our design equation for this circuit. And so the question says we would like to have a gain of 12. So a gain of 12 means this, a gain of 12 means that we must have RF divided by RS is equal to 12. Now, of course, that's one equation with one unknown, so we actually need more information to fully specify our values. And so for that purpose, we can actually choose this sort of fairly arbitrarily, like the precise values don't actually matter. But typically, op-amp circuits use resistors in the range of kilo ohms. So typically from, say, 1 kilo ohm to 10 to maybe 50 kilo ohms or something, that's kind of the rough ballpark that we expect. If you try to use resistors that are too small, then you place too much demand on the op-amp to produce too large a current. And so your circuit's actually not going to work very reliably. So design principle, we want circuits in the range of, typically a few kilo ohms is kind of the bottom end that we would like. So to be consistent with that, we could choose, say, a smaller resistance to be, say, 1 kilo ohm. So let's choose, in this case, RS to be 1 kilo ohm. That would kind of be, that would be fine. That'd be completely useful value. It will still work. But it's kind of on the lower end of what would be viable. And so therefore from our equation, we have RF is equal to 12 times RS, and so that feedback resistor should be 12 kilo ohms. So with these two resistors chosen, we've now actually designed our op-amp circuit. Now the part B of this is, for what range of input voltages will the op-amp remain in its linear regime? So let's remind ourselves what we mean by linear regime. So we talked previously about how an op-amp works, and the output voltage as a function of the difference in the input voltages, so that was Vm minus Vp, where that's Vm and that one is Vp. We previously said that we have this linear regime and then this saturated regime, and this saturated regime is going to occur for an output voltage of the power supply, VCC, and also negative VCC on the other side. So to remind ourselves, this part here is the linear regime, and basically linear regime is good. If the op-amp is in the linear regime, it means it's working as an amplifier. If you go outside that, it's no longer working as an amplifier. So what this is basically saying is, well, how large can the input be and this thing still works as an amplifier? So part B, this question is asking how large can the input be before the op amp stops working as an amplifier. Right? If we go into the saturated regime say up here, you might increase the input voltage, but the output voltage will not increase. We kind of clipped off the signal. So we usually don't want that. So we want to ask how large can this input be? And so the way that we analyze that, basically the critical threshold is output voltage equals VCC. So the threshold is V out equals plus minus VCC. And so for this design, we have, for this design, we have that V out is minus 12 of V in. And so let's look at each of the limits in turn. So for the upper limit, we have V out is equal to positive VCC, which is equal to negative 12 VI. So that is VI is negative VCC divided by 12. So that would be the smallest, the most negative, the most negative input voltage that the output just hits that critical threshold above which it's no longer operating in its linear regime. And the other way around, for the lower limit, we have V out is minus VCC, but also V out is minus 12 times V in, which means that we have VI is positive VCC over 12 for this design. Also, VCC is equal to 15 volts. That was one of our design inputs for this circuit, right? Use plus minus 15 volt power supplies. So we can therefore calculate that V in, substituting in values from before. So let's say largest V in will be 15 divided by 12, which is, bear with me, 15 divided 12 is 1.25. 1.25 volts. And smallest, or most negative, V in would be negative 15 over 12, which would be negative 1.25 volts. So what this means is that the signal must remain inside of this range. So the input must be inside the limits of plus minus 1.25 volts for this amplifier to operate correctly. So we analyze that limit, the sort of range of operation, by just considering what will cause the output to hit that maximum, which is our power supply. And of course we have two limits. There's a positive and the negative limit. So whatever value for the input is going to cause the output to hit those limits, well, that's kind of the largest and smallest possible values that you can choose, or that defines the limits that you can possibly have for your amplifier circuit.